Okay, I don't know if I can follow that kind of energy. I'm sorry, please don't fall asleep. Okay, so hi, I'm Yotam. I'm going to talk about denotational approach to release-acquire concurrency. Where's my pointer? Can't see it anyway. Okay, so this is work with Ohad, Kammar, and Lahav. So what is our goal in this work? We want to design standard monad-based denotational semantics using Brookes-style totally ordered traces for a weak shared memory model. And in particular, about release-acquire. That's the model that we're targeting. So why release-acquire? An important fragment of C. This will be the Brookes traces are adapted to the software model, which means it will have composition parallelism, and also an intricate causal semantics, but not too detailed. So, for example, threads can disagree about the order of writes, non-multi-copy atomicity, but on the other hand, it supports flag-based synchronization, important transformations, and read, modify, write atomicity. So what are these traces? These are linearly ordered traces of state transitions that you can sequence by putting them one after the other, or interleave by taking one transition one at a time until you, oh, it's a bit delayed, I see. Just a moment. Okay, so you take a transition one at a time until you get your interleave transition. Okay, so this starts with Brookes, who defined semantics using these traces for the sequential consistency model. And then Jagadish, Petri, and Riley adapted this to the TSO hardware model. Both of these use the operational semantics of the memory models. TSO is relatively close to sequential consistency. In this work, we're adapting it to the release-acquire model, which is a software model. It has a more complex notion of state. And the important thing here is that this model also has an operational presentation. And this is what we use this fact in order to give such a denotational semantics using these kinds of traces. And it might be surprising that it's possible. Release-acquire, as we said, it's non-multi-copy atomic. So maybe describing it with linear traces is surprising. Okay, so to summarize our contribution, we have directionally adequate denotational semantics, so we can justify using these denotational refinements. And the semantics is based on these linearly ordered traces. It's a standard semantics, so this has all sorts of benefits such as enabling structural transformations. It has higher order functions for free, and so on. And our denotational semantics is abstract enough to justify every transformation discussed in the literature about RA that we know about, but we don't have full abstraction. In order to achieve the abstraction that we do have, there's a new challenge that wasn't previously in Brookes' case. Here, a trace doesn't have an operational interpretation as strictly as it was in the Brookes' case. For us, each trace represents a possible behavior as a kind of rely guarantee sequence. So we're going to talk about that later. Okay. Crash course in release-acquire. First, we're going to look at these two typical examples. So we have store buffering and message passing. In store buffering, we ask the question whether we can read 0 in both of these threads. Let's look at an interleaving to see how this could work. So on the left, we're writing to 1 to x, and then we're reading from y. It's fine, makes sense to read 0. Then we write on the right thread 1 to y, and then we read x. So how is it possible we're reading 0 even though we wrote 1 on the left thread? This is because propagation is not instant. So even though we already wrote 1 to x on the left, it never write to the right thread. This is something that RA supports. On the other hand, we have message passing. So let's again look at this, one of the possible interleavings. Y is reading 1 from the right on the left. And by reading from the left thread, the information propagates. So in this case, it's not possible to read 0 from x afterwards because the information about writing 1 to x propagates that read. Okay, so more concretely, what's going on in this model? The notion of memory is it has a timeline for each location. And rather than just associating a value with each location, it's a bit more complicated. we have these messages that are placed on the timeline. Each thread points to a message. So here is just an example, the T1. And T1 can't, now that it's pointing to X1, for example, it won't be able to access X0 anymore. When it reads from X, it will be able to read at X0. It gets more complicated because messages also point to messages. Views within the causal propagation. So we're going to see this using through an example. Program execution always starts with memory with one those messages. Access we can look at, T1 is writing X1. To do so, it has to place X1 somewhere in the pointing to X0, so it has to put X1 somewhere after X0. Then it has to point to. So the red arrows are the arrows add the new ones. Next, let's look at another axis, the T1, write Y1. And notice here that when it writes this Y1, Y1 points to X1. Okay? Why does that happen? Because T1 pointed to X1. And within the thread, you keep a copy of the view that the thread that wrote the message. You keep that copy inside. And that's what you're going to use to propagate this information forward. First, let's look at T2. It's going to just write a message to X. It doesn't have to place the message after all the other messages. It only has to place the message after where it's pointing to. So this allows the interesting weak behaviors. But now T2 wants to read from Y. So it's pointing to Y0. So it could read from Y0 if it wanted to, but it could advance to a future message on the Y. And now notice that T2 no longer points to X2. It has to advance its view to X1 because it's inheriting the view from the Y message. And this is the propagation of causality that's going on. And now when it's going to read from X, it's because it's pointing after X2. Okay. Well, weak memory is usually presented with top-level parallelism. So what we saw, we had two top threads. But in fact, we wanted our denotations to support the entire language, not just individual threads. So we extended the operational to support first-class parallelism, which means you can have this parallelism construct within the terms. And this allows us to discuss transformations such as generalized sequencing or general laws of parallel programming, and check whether our denotations can or can't support them. Okay, let's move on to the trace-based semantics. So what are the traces in release acquire? So again, each represents a possible behavior as a relay guarantee sequence. We have the sequence of transitions. Previous adaptation to trace-based semantics added a return value in order to handle the functional setting where programs return values. We added the initial and final view to adapt to release acquire. Yes.
What do the letters mean?
Which letters?
The alphas and the mu's and the bar rows.
Yeah, that's where we're getting. Okay. Yeah. So this is a trace. I just you to see it, and now we're gonna go over it in detail. Yeah. Okay. Let's look first at the transition, at the sequence of transitions. What does it stand for? So each letter here is a semantic snapshot of memory. Okay? It's a semantic representation of the memory. So each transition is, we are relying on a specific guarantee of what the memory should look like. And we guarantee to the environment what the memory should look like afterwards without interruption by the environment. So we're relying on mu1 to guarantee row 1, and then the environment can interfere. And we rely on mu2 to guarantee row 2, and so on and so forth. This is like it was in Brookes. Eventually, we also guarantee to return a value to the sequential subsequent environment. What's important to note here, unlike in Brookes, where each transition was literally a sequence of steps in the operational semantics, here it's a bit more nuanced. Right? We're also going to talk about that later. Okay, And the new parts are the initial and final view. So the initial view is how the behavior is relying on the previous environment to keep certain messages revealed. And the final view is how we guarantee, the term guarantees to the subsequent environment not to obscure certain messages. And we don't need in the sequence, we only need them at the beginning and the end, because views only interact with the sequential environment. They don't interact with the parallel environment. Okay, so this understanding of a trace as a rely guarantee sequence warrants some closure rules. These are the closure rules that just adapted to our setting. So you see stutter adds a transition, rely on mu, and then mu. So we're just propagating what we rely on back to the environment. In transitions are combined into one, which means that we're omitting this guarantee of row, and within the transition to keep going within the program the term itself. So now we have a new closure rule specific to array. Rewind means that we're relying on more messages being revealed. So this strengthens what we rely on. And dually, we have forward, in which we're forwarding, thus guaranteeing less messages be revealed. More closure are the notations are closed under. Okay, and how do we compose? Composing larger program terms same way as it did in Brookes for the most part. Sequence interleave in parallel in the same. What's new is, so the final view of the first term needs to equal the initial view of the second term. And when we compose in parallel, the views just need to match, because both subterms and the parallel the same sequential environment before and after. So it makes sense for the view to be the same. Okay, so now we're going to move on to discuss how abstract our denotations turn out to be, which we're going to do using a proxy measure. We don't have full abstraction, but we can get transformations that we know from the literature that should be that hold, and if our denotations can support them. Okay, so it's not the goal of the work to show transformations. It's just a measure of how well the denotations are designed. So the fact that we're using standard semantics, that we the structural equivalences, such as the one here, and also because we have first-class parallelism, we can ask the question of whether we support this transformation, generalized sequencing, or the others, and it turns out we do support all of them. And we also have, with this stutter mumble that we showed, we have some memory access. Read, which we, instead of reading twice, we just read once and copy the result. But some transformations are more tricky. So read elimination, you see that on the left, we have a read that we've eliminated. And well, it makes sense, right? Because we're reading from X, and then we're discarding what we read. But it's a bit more subtle, because in release acquire, maybe reading advanced the view. Therefore, what happens afterwards might be a bit limited, because the view has advanced. So maybe this transformation shouldn't be valid. Okay? But the reason that it is valid is because there is an operational invariant, which says that when you read from the message, for the specific message that you're pointing to, you don't advance the view. So you see here a state that couldn't actually occur in practice. Because here reading from Y1, the T2 reading from Y1 would advance the view. That can happen, and in order for us to justify this transformation in our denotations, we have to be a bit careful, to be more precise. So we internalize this invariant as a requirement on the traces. Only specific things that look like traces can be traces that appear in denotations. Every view within the trace has to point to messages very smaller views. And that way we can support read elimination. We can keep going and look at other transformations that we don't yet seem to support, like write-read reorder. This requires a different consideration. In fact, this is interesting because this one holds even without preserving the state. But not preserved. So why is the state not preserved? If you look at the right term, you see that when we store 1 to x, we already read from y, which means our view might have been larger. So within the message, the view will be larger. On the left, we're storing before we're reading, so there will be a smaller view there. So the state is not the same, but still we're guaranteed that completes the same, we're going to return the same thing. And what's the idea behind this? When you have a message with a larger view, all it's doing is restricting later behavior, because what it's going to read from that message is going to have a larger view, meaning it can see less messages, has less messages available. So the transformation works because on the left, you can just pretend as if you have that restriction, even though you don't. And we want to be able to reason in a similar way within our denotations. So we can't have our traces just correspond to the operational semantics and preserve the state exactly as it is. We need to be more subtle about it. So you see there, if a transition is just actually steps in the operational semantics, it's not going to be able to justify transformations such as this one. So we introduce more abstract closures that decouple us from the operational semantics a little. And we understand them as rewrite rules. So we have pi in the denotation. If we can rewrite pi to tau using these rules, then tau is in the denotation as well. We have 3: absorb, dilute, and tighten. We're only going to talk about the last due to lack of time, which is related to, this is what's going to justify write, read, reorder. Okay, so let's see how this works. We're not going to talk about write order itself. We're going to talk about write, read, deorder, which is the crux of the problem. The rest just follows from laws of parallel programming and structural transformations. So here you see write, read, deorder. Okay, instead of sequencing, you have this parallel composition. And we can look at each and see what happens. So in the left-hand side, where they're sequencing, the views when you right, as we saw before, which means that the initial view of the entire thing might need to be small enough to allow y to read whatever message it wants to read. But on the right-hand side, on the right denotation, the left thread is not as limited, because it could start with a large view, right? And with a large view, use these rewind and forward closure rules that we saw before to synchronize the threads together on the right-hand side. Right? So what happens? On the right-hand side, you have this message with a larger view. On the left-hand side, you might not be able to get that message with a larger view. You have one with a smaller view. And the tighten rule is what allows you to move views within a message forward, tightening making the guarantee weaker. So the trace it now makes a weaker guarantee. That's why it makes sense for such a rule to work. Okay, so this requires, because traces are more nuanced, this requires a new idea in the adequacy proof, but I don't have time to go over it. Maybe you can ask me later. So I'm just going to skip that. We have all of these transformations. Also have more transformations. There's just no room for them. And as I said, we have all the transformations that were discussed in literature. So we're quite happy with the abstraction that we have achieved. So to conclude, we have standard, adequate, and fully compositional or nuanced traces, sufficiently abstract. In doing so, we also extended the view-based machine with compositional parallelism, which wasn't there before. Some limitations. Our language doesn't have a lot of features. Particularly, it doesn't have recursion. We wanted to focus on the problem at hand. We didn't want to add features and make the semantics more complicated. We didn't want to choose which recursion we want to talk about, so we just avoided that problem for now. We don't have a type and effect system. We don't have algebraic representation. We're not covering the full C model. For example, we don't have non-atomics. We don't have full abstraction. So there is some work that we can do. So future directions, one is to address these limitations. For example, we can cover more of C by using more complicated operational semantics, which is called promise semantics. And something else that we're looking into is the relay guarantee traces. So this is quite unrelated to what we're talking about, but we wanted to show you in case someone can recognizes this and knows about this and tell us that we've done before. So here we have explicit relying guarantee we use to represent update and look up algebraic effects. So if anyone recognizes this, please let us know. But that's it. Thank you very much.
Any questions?
Thanks for the talk. So in the end, you mentioned that there was a limitation with having non-recursion, not having recursion. So what would go wrong if you had it, or like what is cannot be covered?
No, I don't know if anything would go wrong. It's just the semantics would be more complicated, and it would be an additional thing you have to think about all the time. And also there are properties like liveness and things that you'd want to consider once you add recursion. And the problem was difficult enough even without recursion. And there are enough interesting examples to talk about like we saw without recursion. So we left recursion aside. That's all.
The obvious question is, why don't you have... Sorry. The obvious question is, why don't you have full abstraction?
First of all, full abstraction with higher order is a difficult problem on its own. But even for first order, Brookes, right? In Brookes' paper, there's if you're familiar, there is full abstraction, but it uses an unrealistic await construction in the language, which you're waiting for a particular state to return a particular state, and that you use that in a context to differentiate terms with different denotations. If you remove that from Brookes, the proof for full abstraction there doesn't work either. Now, maybe we can add such a construct here and have full abstraction, but it will also be maybe even more unrealistic because the state is more complicated here. So full abstraction is also difficult even in first order.
So you're not really saying it's difficult, you're saying it's false.
Yes, it might very well be false, yes. But we don't have a proof that it's false because every transformation that was discussed does hold. Yeah.
Any other questions? Okay, well, maybe I'm not checking the time, but maybe we can stop. Yeah, okay, it's time to stop. So we resume in half an hour, I think. Thanks again, Yotam.